Okay, so last but not least, we have Shaofei from Peking University to tell us about APT attack, right? Detecting APT attack, rather. Shaofei, please.
Okay. Hello, everyone. This is Shaofei Li from Peking University. It's my honor to introduce our recent work, NODLINK, an online system for fine-grained APT attack detection and investigation. This work was completed in collaboration with Huazhong University of Science and Technology, Arizona State University, Case Western Reserve University, and Sangfor Technologies. APT attacks have become a major threat to modern enterprises. Different from traditional malwares, APT have two features, advanced and persistent. The attackers are equipped with diverse attack vectors and may exploit zero-day vulnerabilities, and they often conduct the whole attack in low and slow patterns. These two features always cause existing EDRs failure. To detect and investigate APT attacks, researchers have built promise-based detection systems, which are based on promise log. It is a type of graph-structured auditing log. The system entities are the nodes in the graph, such as process, file, and network. And the system events are the interactions between system entities, such as read, write, and fork. This figure is an example promise graph of APT29. However, detecting APT on promise graph is something like searching for a needle in a haystack, because attack-related logs are much fewer than the normal ones. And in production environments, the detection is conducted with limited resources and the expectation of timeliness. So it is impractical to place the provenance logs into the memory, and the complexity of detection algorithm must be taken into consideration. Generally speaking, the workflow of provenance-based APT detection consists of 3 steps. First, the detection algorithm must determine the attack candidates, which are called the indicator of compromise. Second, construct the attack provenance graph based on the candidates. Finally, conduct comprehensive detection to improve the detection accuracy. In the second phase, previous system can be divided into 2 categories, rule-based and anomaly-based. Rule-based system use manually crafted rules for rule matching. So it is efficient and fine-grained, but susceptible to zero-day attacks. Anomaly-based systems often use neural networks or message passing algorithms, which makes them more generalizable. But they introduce additional computation overhead and is always coarse-grained. Considering the above pros and cons, our goal is to design provenance-based detection system that achieves efficiency, conciseness, and generalizability at the same time. We discovered 2 properties of the attack graph, attack affinity and the attack polymorphism. Attacks are more likely to generate process because attackers need to run malicious hacking tools or access suspicious files and IP addresses. And attack-relevant events are often topologically closed in the provenance graph because attackers need to create the execution chain of attack actions step by step. So to utilize these 2 properties, we propose to model the provenance graph construction as an online standard tree problem. A standard tree is a subgraph that spans a given node site, which are called terminals. For online standard tree, there is an undirected graph with non-negative weight for each edge in the graph. The terminals are online reviewed, and the objective is to minimize the total cost of weights of the solution. Online STP is an NP-complete problem. The optimal approximation algorithm is greedy algorithm. When a terminal arrives, it finds the shortest path from new terminal to the existing solution, and extend the existing solution with a new path. So for APT detection, we can consider IOC or anomaly events as terminals in STP and assign each interaction among system entities with the same non-negative weight. Then the APT detection can be converted to find the subgraph that links all the anomalies with minimum number of edges. In this way, we can get a concise provenance graph with labeled anomaly nodes. However, there are three main challenges. The first is to detect long-term attacks with limited resources. STP requires knowing the whole graph in advance. However, it is impractical to keep all the data in the memory, and using a time window is easy to evade. To address this challenge, we propose an in-memory cache design with a scoring method to prioritize suspicious events. It can preserve the suspicious events in the memory and evict the norm log to the disk. The second is to identify terminals in STP with constraint of timeliness. Existing detection method depends on intensive random walking and message passing on the provenance graph, but it's too heavy. We propose to use inverse document frequency weighted variational autoencoder for terminal identification. It embeds process node and classifies them. Third, applying STP to APT detection requires more efficient algorithms. Existing algorithms need to find the shortest path between the newly arrival terminal and all previous terminals, which is too expensive for online detection. To solve the problem, we design an importance score guided search algorithm for online STP optimization. In the worst case, it only needs to traverse all the edges. To achieve our goal, we design and implement NODLINK, an online detection system that achieves fine-grained detection with timeliness and limited resources based on STP. NODLINK detects anomalies every delta seconds through 4 phases: in-memory cache building, terminal identification, hubset construction, and comprehensive detection. I will introduce how each phase solves the above challenges. For the first challenge, we cannot preserve all the provenance logs in the memory, so we prefer to catch the more suspicious and actively involving graphs. In every time window, we first find the solution of STP on the current provenance graph, which is called hopeset. I will introduce it later in detail. Then, after the cache with the hopeset, we just construct it and merge the hopeset if they have the common nodes. We only preserve top K hopeset in the cache and evict others to the disk. We can retrieve the evicted graph when needed. We prioritize the cache using the energy of hopeset, which is used to evaluate the anomaly of the hopeset. Hopeset anomaly score is the sum of the node anomaly score, and the metric can gradually decay over time if the graph has not been updated. I will introduce how to find the solution in the current time window. To find the solution of STP in the current time window, first is to identify terminals efficiently. NODLINK uses inverse document frequency weighted variational autoencoder to embed process and classify them. It embeds process nodes based on their node level features. We first get the embedding of its command line and the nodes that are directly connected with the process using pre-trained NLP model. We can convert these 3 node level features to sentences in the way listed in the table. Then we calculate the process embedding with IDF weight to make the unusual feature more outstanding. The IDF weight is the ratio of the total number of processes to the number of processes that connected with the specific system entities. After getting the process embedding, we use the historical benign data to train a VAE model offline to learn the normal behavior of processes. Then we can calculate the anomaly score based on the reconstruction error, only to filter out to the suspicious processes as terminals. We introduce the stable value to balance the reconstruction error for unstable processes. The processes with anomaly score higher than the 90th percentile are considered as terminals in the current time window. After identifying the terminals, an efficient approximation algorithm is needed. It is unacceptable to calculate the shortest path as a new terminal arrives. We design an importance-oriented greedy search algorithm to find the solution. It searches for hop set locally and takes advantage of attack polymerism in APT attack. It starts local searching procedure for each terminal with bounded theta nodes, and we call them hop set. Each searching procedure is guided by importance value, which consider both the anomaly and the distance. Anomaly score is the main factor, while the degree is the supplementary factor. We introduce this term because we observe that some processes have the tendency to generate many leaf nodes that do not propagate data and control flow dependencies. These leaf nodes are not interesting for APT attack detection and investigation. Thus, we introduce degree information to deprioritize them. After searching, we merge the hop sets that have the common nodes. Then we can get the approximation solution of STP in the current time window. The complexity of our algorithm is OE plus theta n, and the computed ratio is 2 theta O log k, which is comparable with the optimal greedy algorithm. And the computed ratio is the worst case cost to the cost of an optimal solution. We evaluate NODLINK on 3 closed-world dataset and an open-world dataset. For closed-world dataset, we use the public dataset .RTC and the industrial arena dataset from an internal security engagement of Sangfor and the in-lab dataset collected from our testbeds, which can be accessed via the link below. For open-world dataset, we deploy NODLINK to monitor 10 realistic customers. First, we evaluate the effectiveness of NODLINK. We propose to use 2 metrics, graph-level accuracy and node-level accuracy, to show our conciseness. For node level, NODLINK detects all the attack and only reports 14 false positives, while proof detector and homos report 783 and 416 false positives. For node-level accuracy, the node-level precision is comparable with SOTA offline solution proof detector, and 1 to 3 orders of magnitude higher than homos and unicorn, and it covers 98% of the attacks on average. Second, we evaluate the efficiency by throughput, which is defined as how many system events can be processed per second. As shown in the figure, NODLINK is comparable to rule-based homos, 21 times higher than offline solution proof detector, and 3 times higher than unicorn. It is capable of monitoring 329 hosts, considering that an open world host generates an average of 40 events per second. In the open world experiment, NODLINK detects 7 real attacks in 10 real customers. Here is an example of them. It is an attack that injects executable code to Tomcat and leave a backdoor. Then it uploads the reverse proxy tools, carries out the lateral movement, and collects system information along with the whole procedure. In conclusion, online provenance-based detection systems are preferred over post-mortem ones for detecting APT attacks. We propose NODLINK, an online provenance-based detection system that can achieve efficiency, conciseness, and generalizability at the same time. The key idea of NODLINK is to model the APT attack detection problem as an online standard tree problem. Our experiments show that NODLINK can achieve magnitudes higher detection accuracy with the same or higher throughput compared with 2 SOTA online provenance analysis systems. And our work is open source in GitHub. That's all for my presentation. Thank you for listening, and feel free to ask me any questions.
Any questions from the audience? Yes, please.
great talk. Jiedong Xu from UCLA. I'm curious about the test attributes you are using. Is there any published study showing that how much improvement you can get by leveraging these test features?
Can you repeat it?
Yeah, so I think the other slide shows that you are using a test features, maybe on node or edge, to learn these features, and I want to know how much improvement this part can get.
You mean the IDF weight? Or?
Yeah, I think, yeah.
Yeah. We use IDF weight to make the unusual features more outstanding. So if we remove the IDF weight, the false positive may be more, and just the final false positive can increase rapidly.
Okay, thank you.
Okay.
Hi, thank you for the talk. I had a question about the DARPA TC dataset. The TC is the transparent computing dataset?
Yeah, we use the public dataset DARPA.
Yeah, I've used that too for another publication. I was actually curious about how did you detect what signals map to an APT attack in the log files versus the ones which were not. So how would you know which log entry would map to an APT attack and which APT attack? Because it was all...
Sorry, the volume is a little small.
I was wondering, how did you map the log entries to a specific attack?
Sorry for my listening.
So is it about how to get the ground truth from the TCP?
No, not the ground truth. So I've used that data set, and this is like terabytes of log entries one after another. And they had multiple APT attacks. But which log entry is mapping to which attack? How did you map it? Because log entries would have some would have some signals related to an APT attack, some would not. So I'm wondering, how did you work on that data set? We can take it offline.
Okay. Sorry.
It's okay.
Hi, thank you for the talk. My question is about how NODLINK would handle a case where, so in your Tomcat example, for if more than one APT exploit the same vulnerability, is there a way to untangle the provenance graph in that way? So how do you distinguish when you may have two adversaries, two APTs, both exploiting the same vulnerability or having the same node in the graph?
Yeah, we merge the hope set that they have the common nodes without the additional operations.
Okay, thank you.
I was just curious in terms of testing, how much, what was the size of the data that you used in terms of because generally for provenance data it's very large in an enterprise setting, terabytes of data. So I was curious, how large was the data that you were using?
You ask which data set?
Not which data set. I'm not academic, sorry. Just more, this is something that I've looked at too in an enterprise setting of trying to use provenance data to be able to try to track APTs before. But the problem is that generally the data that you're going across is very, very large. So I was just curious, how large was the data, in terms of gigabytes, terabytes, whatever y'all were using?
Yeah, the DARPA TC data set is of the size of 50 GB, and our testbed collected data is around 10 GB. Yeah.
Okay, thank you.
Yeah, so hi, I'm Carlo Wu from Stony Brook University. So from what I understand correctly, one of the ideas of your work is, trying to store abnormal like flows in memory,
Yeah.
and then the other ones you kick it to disk, right?
Yeah.
And I was just thinking, knowing about this technique, is it possible for an attacker to craft like a semi-abnormal like flow, and then to keep your online algorithm busy while keeping the real attacks not detected in this case?
Yeah, this is a feature of APT attacks. It may the attack actions may take a long time. So the .partic, the data set has this behavior. So for memory cache, we can retrieve the evicted graphs when needed, because if we encounter a node that we see before but not in the memory, we can retrieve it from the disk. Yeah.
So it is not deleted, but it's still kept.
And not
in
deleted.
case
It is stored in the database.
Okay.
Okay.
Thank you.
Thank you.
Let's thank the speaker again.